Bismillahirrahmanirrahim. Assalamualaikum. Today we are going to talk about another paper and how we can do the same work in simulation. I will explain, and I'll explain also what are the procedure and how the design procedure was completed during the generation of the sensor model. This will be a transmission line-based sensor. Today we'll talk about the machine learning enhanced material sensor for real-time insoluble particle position movement in multi-phase oil flow. So the thing is, we used machine learning to improve the result of the sensor, not to optimize the sensor structure or the metamaterial. We used machine learning to distinguish between the error and actual result, and we also use machine learning to classify the sensors performance. I will explain the things later on. Now I'm just telling you the basic things. So multiphase mean there are more than one liquid flowing in a flow. So there is no solution, but it is a mixture of liquids or mixture of some materials like oil and water and air bubble. They don't make a solution usually. So this is a multiphase flow. This paper was published in IEEE Transitions. So let me go to the paper. So I'm talking about this one. So in this paper, we have used some algorithms, machine learning algorithms. I will also share those algorithms with you. I mean, the file and where you can find them is in my ResearchGate profile. So also in my, I think, in my in my Google Scholar and ResearchGate profile. So here you can see this paper. So I'll be showing you a earlier version of this one because this is a subscription-based paper. So I will show you a earlier version, earlier draft of this paper. So let's go to the paper. This is a very first draft that I have created. So here you can see that we designed a metamaterial-based sensor like this, and then we get a result similar to this one. And then we did some study about the isolation and the E field and H field. So here you can see that every resonator, there are four resonators, four metamaterial resonators, and every resonator has a designated or distinguished resonating frequency peak. So here you can see when there was only one resonator, the resonator was resonating at this frequency only. When there was two, the second one created a new resonating frequency in this frequency range around 3.6 GHz, and the third one created a frequency range here, and also fourth one created a final fourth one, our final design created four different resonating frequencies. So this whatever happens to this this metamaterial resonator will change this frequency, resonating frequency, and whatever happened here will change this frequency range, and whatever happens here will change this frequency range, and whatever happens to this one will uh, affect this resonator frequency. Actually, uh, yeah, I mean, uh, there is a little bit there is some mistakes. So here you can see there is some mistakes actually in this paper. This image was fixed later on because um, it should be the otherwise. Like this one is responsible for only this resonative frequency. Okay, I have to fix this one. So So whatever happened to this one, this metamaterial, will affect this resonating frequency. If you put your finger on top of this sensor, let's say, this resonant frequency will shift, but the rest three will not change. Let's say you keep a finger on this metamaterial, only this one will change its position or show some effect, but these four should remain the same. This way we can identify that which metamaterial is being affected by seeing the change in the resonative frequency. So this way you can identify by seeing this resonating frequency graph, identify the position of something. Let's say a let's say a oil is flowing on top of four of them, four of the resonators. There is some impurities in that oil, let's say a droplet of water. So if the droplet stacks on top of this sensor and this metamaterial, we can see that only the this resonant frequency will change from its original position, but the rest of the three will remain as it was. Similarly, if the water droplet is out of this resonator, only this resonative frequency will show some changes, but other three will not show any change. Similarly, if you don't see the sensor and if you don't know where is the position of the droplet, water droplet, you just see here and see that only suddenly this resonative frequency is moved or changed its position. You can assume that the water droplet is on top of the second resonator, like on top of this one, because this resonative frequency is generating by this resonator. So if it is changing, that means something here is also changing. So this is the main concept of this paper. So here you can see every resonator has a this designated frequency. At only that frequency this sensor resonates and other sensor remains insensitive. This is E field and this is H field, and this one is the sensor setup. I just told you that the let's consider oil is flowing on top of the sensor and there is a water droplet. So we in the simulation we did the same thing. Sometimes we used air, sometimes we used oil. So this is the experimental setup, and here you can see the comparison between the simulation and the measurements. So this is the simulated result. We will only explain this source. This is the measurement result. We cannot explain this one because we will not show you the measurement. I'll just show you how we can generate this type of images. Okay. So here you can see that changes around which resonating frequency shows the most changes in this thing. You can see from this graph. Later on in the final paper, I think this graph was not included. Okay. Then we use machine learning algorithms to identify the result. I mean, from this image, you can easily see that only this resonating frequency is changing. So you can understand that water droplet or bubble is on top of the sensor related to this resonative frequency. Here you can see only this one is changing. So we can assume that the metamaterial resonator, which is responsible for this resonating frequency having some changes, like the water droplet is or like the bubble is on top of this one. This is simulation, so it is very easy to identify the changes, but when we go for measurement, we can see that every peak is changing. Here you can see that you cannot really understand which one is actually changing. I mean, you can understand because you see the pattern. The resonating frequency, all of them shifted to a lower frequency range. Only this one shifted to a higher frequency ranges. So this one is showing a different characteristics. Similarly to this one, here you can see this is almost the same. This one moved forward. This one moved backward. this one maintained this position almost the same, but it shows a little bit of change. So it is very difficult for us to identify which one is actually from this graph. It is very difficult to understand which is the position of the water droplet. Similarly, here you can see every resonator frequency moved a little bit to the lower frequency ranges. Only this one moved the highest, this one experiencing the highest shift. So we can say that this one is showing a little bit different characteristics. That's why we can say that the water droplet is on top here, but the actual scenario was like the water droplet was on top of this one. So why is this happening during the measurement? This is happening because the oil we used actual oil. So as you already know that oil, the active property of oil is not same everywhere. So even you take same oil from a same brand, but measure the property in two position, you'll get different values. That's why whenever you flow only oil, because due to the fluctuation of dielectric property in the oil itself, the shift and the sensor will show some frequency movement. That's why we cannot only rely on the resonative frequency graphs. To overcome this environmental effect, we used machine learning algorithms to train a algorithm to identify from a dataset. We give the machine learning this dataset, like how much shift one resonative frequency is experiencing. Then machine learning will tell us that which the insoluble particle. By using insoluble particle, I mean water or oil in our case. So by examining this data, machine learning algorithm will tell yes, the data are presented, it is in not horizontally, it is vertically. So band 1 is the band 1, band 2 is this one, band 3 is this one, and band 4 is this one. Yep. So when there was no air bubble, only the oil was flowing, the resonant frequencies were generally here. Okay, so when we put a air bubble on top of this one, the resonators which is assigned for this frequency, the data is given here. So you can see that only this one showed the, let's say this one is moving on the positive side, this one is okay. This one is showing the highest shift between all of them. So we can identify, or we can say that this is where uh, the air bubble is. Similarly here, when this one experiencing the most amount of shift, this one is experiencing the most, and this one is only experiencing a shift in the negative side and in the positive side. Okay, so okay, actually this line was for this graph, my mistake, and this one is for this one. So here you can see in this table that this graph is for this one, this one is for the second one, and the third one is for third DMS, and fourth one is for fourth DMS. So you can see when there is no air bubble, only the oil, and the resonative frequencies are this one. So when we put a air bubble on top of the sensor 4, that means the resonator designated for this resonative frequency, this one is experiencing the most amount of shift. So you can see here. So the machine learning algorithm will tell you that air bubble is on top of cell 4. Okay. Similarly, for water droplet, you can see the same changes. So here you can see that there are 5 algorithms we have applied. In our video, YouTube video, we will just only show you the procedure for one algorithm. The procedure is for all the five algorithms is same, and you'll find the code in my Google Scholar profile, so you can use that code to create a uh, similar experimental setup. And I will also show you how we can get the peak value from CST data tables using MATLAB codes, and I will also show you the code. So I will not use this code in this video. I will explain the process in a later video. Okay, so let's go to CST. Here you can see the final design of the sensor, and here you can see the resonating frequencies. Let's say, okay, this curve is this one. Yep, yep. And here you can see the only one resonator is resonating at this frequency. So only this one is resonating here, only the third one, and here only the fourth one is resonating. So you can say that the sensor is properly isolated. So any effect for this resonator will not mostly affect the resonator or the any characteristics of these resonators. So let's go and make the design. As we are making a transmission line based sensor, we will use antenna setup. So now you can simulate the result. Okay. First, you have to simulate once to know the resonative frequencies, and after you know the resonative frequency, then you can use field monitor and see the H field and E field. But as we have already simulated the same result, same structure, so I think we know the resonative frequencies. So what I will do is I will get the resonative frequencies from this previously simulated sensor. Here you can see this one is this is the same thing. I just created and simulated this one because just for the sake of saving time. So I will get the result from here, and I will show you one example how to assign E field and H field. So here you can see the resonant frequency is resonating at 3.5. Okay, let's do for all. Done. So here you can see there are three field monitors for all frequency ranges. So if you simulate now, it will simulate and give you this exact same results. Okay. Now what I wanted to show you is how we can make this I mean um, the oil setup, right? Okay. So to make the setup, first I want to copy this one so I can know the measurements and then paste. Okay. As we are using this one for measurementing. Just press it. Okay. So now it has a diameter. This is the pipeline. As we are trying to do as much as to regenerate as much as close possible to a setup that is more similar to this one, the actual measurement. So we will just not put oil on top of the sensor. We'll also design the pipeline and then put the oil. So this one has a diameter of 11, right? 11, and inside it has 9. Then that means the thickness is 1 millimeter. Okay, and oil is not important. I think nothing is more important now. Okay. Close. So let's design a new component and make cylinder. Okay, one other thing we should see is the length from here to here. It is 180. Okay, so I got 11, right? 11. So we're making 11, and we'll fix that later on. 1. Okay, everything is fine. 180. Material. Materials. Polycarbonate. So let's give it polycarbonate. We are using lossy because every actual material is lossy. Okay, now we have created the pipe, and then we will also create the let's bring it to the middle so that our designing gets easier. Now I think, yep, it'll be easier now. Okay. One maybe. Oops. I think it is almost okay. 180. Let's keep it, make it a little bit smaller than the. Okay. Let's make oil. So now we have our pipe. Let's just rotate this one. Okay, before rotating, we should do another thing. We also need a air bubble inside, right? So let's design that one. Let's say it is millimeter. There is a air bubble. So let's give air and press. Yep. So it is telling us to cut. We will not cut. Okay. Now it is overlapping with the oil. So the air bubble is inside the oil. So it will uh, trim insert the highlight shape. Let's say I forgot this one. Okay. It's difficult to see. So let's hide the pipeline. And as you can see, the water droplet is with the, yeah. But for our easy controlling, let's keep it in the middle. So let's move it. Yeah. Now everything is as we are planning to do. So now we'll rotate this one. Place it on top of the sensor. You can touch the surface if you want, but if you don't, keep it close, that's enough. So now everything is ready for our sake, I will hide this one because I cannot see. So now you can see everything. Okay. For sensing setup, what we will do is to get a result like this one for air. Okay. For this type of result, what we will do, I mean, our plan is to put the air. Okay. Our plan is to put the air bubble on top of the sensors, right? To test the effect on top of sensor 1, we will keep this is the air bubble. Let's apply. See, so to put the air bubble on top of sensor 1, effect of water bubble, or like since the position, we will move the the air bubble on top of each sensor. Like first we'll keep the air droplet here, then we will move it to on top of this sensor, and later on here, and later on here, and later on outside everything. Okay, so now for that I will use parameter swap. Okay. I'll use a parameter swap to move. Okay, so I will assign a parameter swap here, like let's call it move, and set apply. Now we give it 0. So let's get a notepad. So if I put it here, it will be 14, right? So 14, I'm just taking the values for later use, and if you move it here, it is 30, yeah, okay, 30. And then if I move it here, it should be 14, okay, 44, 44, and then let's put it here 66. Okay, 66. Good. Close this one and go home. Use parameter swap. New sequence, new parameter. There is only one from 0. Use arbitrary point because we are giving exact positions. So now give it here from 0 to this. Okay, so let's check if it's working on. This is for 0, this is for 30, and yeah, so far everything is good. So after you simulate the thing, it will give you a result like this. So what does it mean is the position is slightly bit different for my simulation. Let's consider there was no bubble in this position. So it is for 66. I mean when the bubble was outside, you'll get the result like this. This is the reference result for our when there was no bubble, only oil on top of the sensor, like this one, like this. There is no bubble. There is no bubble on top of any resonator. The sensor will give a result like this. And when the bubble is on top of the resonating frequency assigned for resonating resonators assigned for this frequency, like this one is the smallest. So let's say the bubble is on like here. You'll see only this frequency range is changing because the bubble is now on top of this sensor, and rest 3 is not moving because there is only oil, so there should not be any change. Similarly, when the bubble is moving to the second one, it should give a value in the second one. See, the orange is the new one, and the brownish one is the one when there is only oil on top of the sensor. So you can see that the second one is showing the change. For the third one, this is the this is the third one. So for this, the bubble is here on top of this one. So here you can see only this one is moving, and for the last one only this one is moving when the bubble was on top of this one here. Okay, so this is how you identify the position of the resonators by viewing the resonator frequency. So if you see a graph like this one, and you know the resonator frequency, the reference frequency is the brownish one, and you see there is only one peak is shifting, so you can definitely understand that the bubble is on top of on the sensor which is making this resonator frequency. Okay, so now you understand the concept of this result. So what you will do now to use machine learning, you will extract this result, go post-processing, and extract plot data. Let's say air. This one is air, right? AIR. Okay, save. So I think you have a data set of air. Yeah, you can see there are 5 simulation data. So we will open it using Excel. So now I want to use the data sector from Excel and CSV. Okay. Oh, sorry. So here you have I think the result for 5 simulations. Yeah, this one is the second one when the position is on top of 22. So we don't need all of them from throughout this all data. We'll only collect 5 or 4 datas. Like we will collect these 4 top frequencies. So should be looking from 3 to 44.5. From 3, find the best one. So here the lowest is this one at at 3.2 GHz. So let's make a new table. We will copy this one, paste here, and go back. Let's find the second peak. So it should be at around 3.25. Yeah, 3.25. This one, right? So we'll take the frequency again, put it in the second block, and then it should be at almost close to 4. I think this one, not this one. Yep. So we'll take the frequency, and then it should be 4.3 or something. This one, right? Okay. Okay. So now you have for data when there is no sample. So let's say no air bubble. So this is 0. So let's do for the next one. It should be around 3, right? Okay. Copy, paste it here. Actually, there is a MATLAB code that I used to this to make this process automatic. I think I have missed one. Yeah, to make this process automatic, and I will show you how you can also use that one to do this process automatic. I miscopied this one. And then the fourth one should be near 4 kHz. Yeah, this one. Okay, now you have another data when the sensor when the air bubble is on top of the fourth sensor, right? Okay, this is how you collect all data, and for machine learning you need at least some big amount of data. So you need to simulate the sensor simulation at least let's say 100 times. For that case, use more points in simulation. Let's close this one. What I'm trying to say is that delete this one, new parameter, this one, from 0 to 100, and samples 100. So you will get 100 simulation and you will get 100 sets of data. This is how you can create more data for simulation from simulation. Okay. So now I will show you using this same format how you can train the train the machine learning after the simulation, like 100 or something. So for you, I have prepared a data sheet. Here you can see that this is for I think 60 or 75 simulations. So I'll use this one to create the machine learning procedure. Okay. So here is the codes. It's very simple and straightforward code. It will just classify the data into 4 classes and give you the answer which data belongs to which sensor response. So here you can see the accuracy is almost like 93% for neural network. So let me delete this one. Okay. So what you will do, you will collect and customize your code. Here you can see if you have more than 4 resonators. Like if you have 3 or 6, you need to change some codes from this line, and also I think from, no, not from here, I think that one. Yep, I have to change that one. Okay, to customize as you need. So what I will do, I'll bring this one. Let's go to the desktop. Let's paste it here. Okay, now copy the path, copy path, and paste it here. It will be the same because I have used the same thing. So let's paste it here. Control V. So now if you run, so you can see that the code is running, and you'll get the accuracy curve and the confusion matrix. So this is how you can train an algorithm and then produce a comparison accuracy to make the procedure error free, and also make the procedure also human free also. So this is how you can use your simulation data for neural network or machine learning algorithms. And now you can actually in this graph you can see that I have used similar data from here. The value of change, you can also use detect frequency also, like this one. This type of results also give you the same almost the same accuracy, so you don't need to worry about that one. Okay, so far and you will find the code in my ResearchGate profile or in this link also. Yep. Here is the code, you can see, and there are some data also for, oh okay, if you go to this UI, then you will find also some data in the for your practice. Okay, so far I have completed explanation of this one. I'll make another video for explaining in details how we can use MATLAB code to collect the data and then simulate it here. Okay, so far this concludes the video. I think those explanation video helps you a lot. Assalamu alaikum warahmatullah.